Welcome back. So we have been looking at counting problems. In particular, we have been looking at problems in combinatorics, which is a branch of mathematics that involves counting. So the typical question that one asks is, given a set, what is the cardinality of the set S? Now the question is that how is the set given? Of course, if the set is given explicitly, then counting the number of elements in S is quite simple. But most of the time the set is described in words or it's described in some other way. And in that case, the set is basically given implicitly and counting the number of elements in the set is a pretty challenging problem. For example, how many elements are there satisfying a particular set of conditions? Or equivalently, how many ways can you draw an element from a set of universe satisfying a certain set of conditions? So these are the kind of questions that usually we look at. So we have been looking at a few examples. For example, how many n-digit numbers are there? There are no consecutive digits are same. How many non-decreasing functions are there from 1 to n to 1 to k? How can you distribute n identical toffees among k kids? And finally, how many 0-1 strings are there of length n which does not have any consecutive 0? Now, the problem with counting is that every problem is unique and it requires a different technique to solve it. It is one of the most challenging subjects in mathematics. Some big names like Srinivasa Ramanujan also worked on counting. And there are some handy tricks and tools to attack, but they are just some kind of a small tools. It doesn't exactly give a very standard way of solving all the problems. So one such tools or tricks was this particular special case when we cause how many ways can we select k objects from n objects. So there are two different cases that we have to take in. Number one is whether the objects are, or whether repetitions is allowed. In other words, can I pick a same object from the n objects multiple times? And the second case that we should look at is whether the order in which the elements are picked matter. And this gives us these four cases, and we have seen how to solve these four cases. Another problem of this kind is how many ways can one distribute n balls into k bins. And there are certain cases which to be handled. For example, whether the bins are distinguishable, whether the balls are distinguishable. If the balls are distinguishable, does the ordering in the bins matter? Can some of the bins be empty? And are there some other restrictions? And here also we kind of solved them or kind of gave you the idea of most of the various cases, except for this particular case, which is P and K, which is a pretty complicated case by itself. And we saw it last video that this is one of the this is a very challenging problem, something that Srinivasa Ramanujan had worked on. Now, using all these tools and tricks, we did look at these problems and we got to see how to solve these top three problems. Now, the question that I have is how to solve the last problem, namely number of 0-1 strings of length n which does not have any consecutive 0. right? Now you can try it out by yourself and realize that none of the standard tricks actually help here. It is in fact quite complicated to count the number of 0, 1 string of length n, which doesn't contain a non-zero, which doesn't contain any consecutive zero. So let's try to see how can we break this one. So let's Tn be the number of 0, 1 string of length n which does not have any consecutive zeros. So it's parameterized by the number n. The question is that can we answer this Tn for small values of n? So what is T1? So T1 of course says that it is the number of 0, 1 string of length 1 that doesn't contain any consecutive zero. Of course there can be two of them, maybe 0 is one of them and 1 is the other. So this answer is 2. What about T2? Again I can have 0, 0, 1, 1, 0, 1, 1, but 0, 0 I cannot have, right? Because 0, 0 has consecutive zero. So the length of number of strings of length 2 which doesn't contain a consecutive zero is 3. So like this we can possibly even count what is T3, what is T4 and so on. But that is a very bad way of doing it. The question is that if somehow I know how to count T1 to Tn minus 1, is there a way of computing Tn? So it's kind of like the induction hypothesis or induction step. That to count Tn, first count T1 to Tn minus 1 and then using them can we somehow get an estimate of Tn. So let's see. So this is the problem and Tn is the number of 0, 1 string of length n. Now consider a 0, 1 string of length n which does not contain any non-zero, any consecutive non-zero. How does it look like? It is something of the form x1, x2 till xn, right? It doesn't contain any consecutive non-zero. So I will break it up into two cases. Of course, the cases will be depending on whether the last number xn is 1 or 0. So let's see. So the case 1 is the last bit is 1 and case 2 is last bit is 0. And then what we will do is that we will try to compute the number of elements satisfying case 1 and number of elements satisfying case 2. In other words, we will count the number of 0, 1 string of length n which doesn't contain any consecutive 0 and last bit is 1. That is basically the size of case 1. And similarly for case 2, we will compute the number of 0, 1 string of length n which does not have any consecutive zeros and last bit is 1. Note that these two cases are disjoint, meaning a string can be in either in case 1 or in case 2 and it has to be in one of them. Right. So if I can compute case 1 and case 2, then I can get the whole answer as sum of the number in case 1 plus sum of the number in case 2. And that's the way we will proceed forward. So let's look at the first case. Case 1, the last bit is 1. Now the question is that how many 0, 1 string of length n are there which does not have any consecutive 0 and the last bit is 1. Now let x1 to xn be a 0, 1 string of length n, actually this should be n, which does not have any consecutive 0 and xn equals to 1. So how does it look like? So this one is 1. Now what happens to the rest of them? So let me draw it again here. So I have x1, x2 till xn minus 1 and xn. Now x1 is 1. So what are these possible? I claim that you put any number x1 to xn minus 1 such that it satisfies the condition that it doesn't contain any non-zero string. I can add a 1 at the end and I get one of these cases. So clearly one thing is that x1 to xn minus 1 is a string of length n minus 1 that doesn't contain any consecutive zeros. Because if there are no consecutive zeros between x1 to xn, there is clearly no consecutive zeros between x1 to xn minus 1. Right? So you can tick. So x1 to xn minus 1 is a string of length n minus 1 that doesn't contain any consecutive zeros. And in fact, it is also the other way, meaning give me any string of length n minus 1 that does not contain any consecutive 0. I can add a 1 at the end and get a string of length n that does not contain any consecutive 0 and whose last bit is 1. Why is it so? Because by adding this 1, the only time I can cause a problem is by creating a consecutive 0. But since this last bit is 1, so whatever happens with the bit before that, I don't care. These two bits together cannot be a consecutive 0 ever because this is 1. So this cannot happen, right? So in other words, what do I have? In other words, this x1 to xn minus 1 is a 0, 1 string of length n minus 1 which does not have consecutive 0, and any such string can be converted into a 0, 1 string of length n that doesn't contain a consecutive zeros and last bit is 1. So the answer for this one is Tn minus 1. Note that this is follows. This is exactly the definition of Tn minus 1. Right? So the size of case 1 or size of number of elements that satisfies case 1 is actually Tn minus 1. Correct? Now let's move to the second case, case 2, in which case the last bit is 0. Again, we want to compute now the number of 0, 1 string of length n that does not have any consecutive 0 and last bit is 0. So let's x1 to xn be a 0, 1 string of length n which does not have a consecutive 0 and the last bit is 0. That means xn is 0. Now what happens here? Let's see. So I have xn minus 1 and xn. Now if this one is 0, can xn minus 1 be 0? No, it cannot be. Because if it was 0, then I would have got two consecutive zeros. Xn minus 1 and xn are two consecutive numbers that are 0. So from this definition of x1 to xn minus xn, I know that xn minus 1 is 1. Now if xn minus x1 to 1, now let's go to xn minus 2. What happens here, x1 to xn minus 2? Now just like we did for the last case, we realize that x1 to xn minus 2 is now a string of length n minus 2 that doesn't have any consecutive ones. These are consecutive zeros. And more importantly, any string of length n minus 2 that does not contain any consecutive zero, I can add a 1 and a 0 at the back to get a string that satisfies case 2. So in other words, we have that xn minus 1 must be 1, which means that x1 to xn minus 2 is a string of length, this is n minus 2, which doesn't contain any consecutive 0, and hence the answer is tn minus 2. Now, with this, can we do something? Now, can we combine them to get some results? Let's see, what do we have? We started with this value of tn, and we split up this whole set of strings of length n into two cases. Case 1, for which we realize that now that the number of elements in case 1 is tn minus 1. We had case 2, or last bit is 0, in which case the number of elements was tn minus 2, and therefore tn is equals to tn minus 1 plus tn minus 2. Right? Now this doesn't exactly solve the whole problem. What does it do? So I told that, okay, if this is tn, I have got t1 equals to 1, I have got t2 equals to 2, and I also have got the recurrence that tn equals to tn minus 1 plus tn minus 2. Note that by doing so, I can now just keep on, I can find out tn by repeating this process multiple times. For example, what is t3? T3 is t2 plus t1, which is 5. What is t4? T4 is t3 plus t2, which is 8. What is t5? T5 is t4 plus t3, which is 13, and so on. Right? So this way, I have been able to count what the value of tn is. I found out a nice way of computing or counting the number of elements of length n, number of strings of length n of 0, 1, which doesn't contain any consecutive zeros. Right? So this is a nice way of counting it. But the question one can ask is, can you come up with a better procedure of computing tn, or do I have to keep on applying this process again and again and again n times before I get tn? Why can't we get some answer like tn equals to 2 power n by n or something like that, like we got for the case of the distribution of n things into n balls into cave brains and so on? Can't we get a closed form expression of for tn? So this brings us to this problem of recurrence relation. So recurrence relation is a subject. So according to Wikipedia, this is a quotation from Wikipedia. In mathematics, a recurrence relation is an equation that recursively defines a sequence or multidimensional array of values. Once one or more initial terms are given, Each further term of the sequence is defined as a function of the preceding terms. Let's go back and let's see that this is actually a recurrence relation. I have been given the initial terms, which are these, and this is how I solve Tn by looking at the preceding relations, preceding numbers. In fact, recurrence relation is used extensively for combinatorics, analysis of algorithms, computational biology, in theoretical economics, and many other subjects. Recurrence relations are used for modeling problems, particularly counting problems like we saw today, and it is also a big use of recurrence relation is that one can solve recurrence relations easily. Namely, one can get some compact forms for these Tn's and so on. In the next video lecture, we will see one more example of application of recurrence relations for counting, and after that we will be going into how to solve recurrence relations. Thank you.